Chapter 5, Mechanics of Beams and Diaphragms. We need this knowledge to understand the operation of many mechanical sensors, such as pressure sensors, microphones, accelerometers, and so on. In addition, nowadays, many jobs or careers are multidisciplinary, so it will be very beneficial for electrical engineers to learn some fundamental knowledge of mechanical engineering.
Let's first discuss some very basic mechanical concepts, such as axial stress and strain, which we have already discussed previously. So we apply a force F to stretch the object shown in this figure. Its original length L naught is changed to L naught plus delta L. So this delta L is the change of the length. Then the mechanical strain epsilon is defined as delta L over L naught. And the stress sigma is defined as F over A, where F is the force, A is a cross-sectional area. So stress is a force per unit area, a Newton per meter square, Pascal. That's the unit for mechanical stress. And if this beam is stretched, the strain and the stress are positive, right? Because delta L is positive, right? It's increase of length. So we have positive delta L. If this beam is compressed, right? If it's in contraction, then the strain and the stress are negative, right? Because delta L is negative. And the Young's modulus, modulus of the material, E is defined as the ratio of stress over strain, right? Namely sigma over epsilon. Right? This Young's modulus is typically constant. But then the stress is linearly proportional to strain. Right? There's a simple linear relationship between stress and strain. And the coefficient is Young's modulus. This is actually Hooke's law for 1D case. Questions? Poisson's ratio. But note that the longitudinal elongation, right, if we stretch this beam in longitudinal direction, is accompanied by the transverse contraction, right, typically. As shown in this figure, we can see that, right, if the longitudinal length is increased to L plus delta L, right, the transverse dimension D naught is changed to delta D naught plus delta D. So delta D is the change of the transverse dimension. So similar to the longitudinal strain, we can define the transverse strain epsilon sub t as delta D over D naught. Right, so the longitudinal strain is along the longitudinal direction. The transverse strain is along the transverse direction. What's the sign of epsilon t? Right, if epsilon L is positive, if epsilon L is positive, which means this beam is stretched, right? So delta L is positive. Then what's the sign of delta D? Right, typically it's negative, right? The dimension will decrease in the transverse direction. Right, so delta D is negative. Then epsilon t is negative. So epsilon L and epsilon t have different sign, opposite signs typically. The Poisson's ratio, nu, right? Please note that this is not V, this is the Greek letter nu. This Poisson's ratio is defined as a negative transverse strain divided by longitudinal strain, namely negative epsilon T over epsilon L. So what's the sign of nu? Right, it's a positive, right? Because epsilon T is negative. If epsilon L is positive, then we have two negative signs here, and they cancel with each other. So eventually, the sign for nu is a positive. And the typical value of Poisson's ratio is somewhere between 0.1 and 0.45. But for example, the Poisson's ratio of polysilicon let me change your okay. The Poisson's ratio is 0.22, right? This means if the longitudinal strain is 1%, then the resulting transverse strain will be negative 0.22%. So that's the ratio between transverse strain and the longitudinal strain. Next, shear stress and strain. Please note that if the force F is applied perpendicular to the surface, right, this force is called a normal force or axial force. Okay, that's a normal force or axial force. And the resulting stress or strain are called axial stress and strain. If the force is parallel to the surface, such as this one, this force is called shear force. And then the shear stress, tau, is defined as F over A. Again, the force per unit area. Right? So the shear stress is simply the shear force divided by the surface area. Its unit is Newton per meter square or Pascal, right? Same as the axial stress. And the resulting strain, gamma, is defined as delta x over L naught. Note that delta x is a displacement of the top surface. Right, this is delta x, and L naught is this distance. Right, so gamma, right, shear strain defined as delta x over L. Right, that's simply equal to tangent theta. Right, theta is this angle. Right, so shear strain is actually an angle, a tangent theta. And if theta is very small, tangent theta is approximately equal to theta. Right, so for small deformation, right, the shear strain is simply equal to this this kind of deformation angle or the shear angle. Right, so that's the shear strain. We can define a shear modulus of elasticity, G. Right? G is defined as a shear stress over the shear displacement angle, namely the shear strain. Right? So it's tau over gamma. So it's a shear stress over shear strain. So this definition is is similar to the definition of Young's modulus. Right? Young's modulus is defined as the axial stress over axial strain. Right? G is a shear stress over shear strain. And it's not surprising that G and E are related. Right? Actually, G is equal to E, the Young's modulus, divided by 2 times 1 plus nu. Right? Nu is a Poisson's ratio. So we can see there's a shear modulus G is typically less than E. Right? G is less than E. Questions? Okay, next let's take a look at a 3D case. Right? We can see in this 3D case, there are 3 normal stresses and 3 shear stresses. The 3 normal stresses are sigma 1, sigma 2, and then sigma 3, right? Along x, y, z direction. Those are the 3 normal stresses. Right? We can say they are perpendicular to the cubic surfaces. Right? X direction, y direction, and z direction. So 3 normal stresses. And there are also 3 shear stresses. Tau 1, tau 2, and tau 3. Right? They are parallel to the cubic surfaces. So totally 3 normal stresses and 3 shear stresses. Yield strength and yield strain. This figure plots the stress strain curve of a typical ductile material. The vertical axis is stress. The horizontal axis is elongation or strain. We typically use a percentage to represent strain. And we can observe that the area between point 1 and point 2, this curve is almost a linear, okay, almost a linear curve. And this region is called the elastic region, right? Elastic region. And previously we defined the Young's modulus, right? Which is defined as the stress over strain. Right? Then we found this figure. We can see that Young's modulus is simply the slope of this curve of the stress versus strain curve. Right? So actually, Young's modulus is defined in this elastic region, right? Which where this slope is almost constant. And the point 2 is called the proportional limit or elastic limit. And the point 3 is called yield point, right? And the stress and the strain of this point are typically called yield strength and yield strain. So this point is called a yield point, or we can say that above this point, or close to this point, above this point, the material yields. Okay, it leaves this elastic region, and the area between point 2 and 5 is known as a plastic region. Right? This first region, elastic region, between point 2 and 5 is an elastic region, right? Because beyond the point 2, right, the material will undergo plastic deformation or inelastic deformation, and the material will not return to its original shape if the external force is removed, right? If they enters this region. And the point 4 is the point of ultimate tensile strength. Okay? We can see if we consider the vertical axis of this point, right? It gives us the maximum tensile strength of the material. We can draw a horizontal line to find out the maximum tensile strength, right, from this point. And the point 5 is the fracture point, at which failure of the material occurs, right? The material simply fractures. Right, so this is the typical stress strain curve of a ductile material. And the yield strain or yield stress, right, are the maximum strain or stress before plastic deformation. And for brittle materials, right, this figure plots the stress strain curve of a typical brittle material. We can see it's different from that of a ductile material, right? They usually, right, for brittle materials, they usually yield catastrophically rather than plastic deformation. So they do not have this plastic region, right, from point 2 to point 5. It actually fractured or failed right at point 2. So in this case, the yield strain and the yield strength are also called the fracture strain and the fracture strength. Please know that for ductile material, yield strain and yield stress are different from fracture strain and fracture strength, right? Because point 3 and point 5 are different, right? 2 different points. For ductile materials, right, this point actually overlap together. So the yield strain or strength is same as a fracture strain or strength. Right, so that's the difference between ductile material and brittle materials. Questions? Okay, next, let's discuss the bending of beams. And here we assume that the length of the beam is much larger than its transverse dimension. Namely, L is much greater than W and H. So it's a slender beam. Let's first introduce the types of support. Let's consider the cantilever beam shown in this figure. This x-axis is a horizontal position. It represents horizontal position, and its origin is selected at the anchoring point. Right, that's a 0. The W is the displacement of the beam. Right, we can see it will be a function of x. And the left end of this cantilever beam is a fixed support. we call left and fixed support. Or it's fixed, or it's also called clamped or built-in support. We have different names for this support. Mathematically, fixed support means that W0 is 0. Right? W is displacement of the beam. Right? So this equation basically tells us that the displacement of the beam at this support, okay, at this support is 0. There's no displacement, right? At x equal to 0, right? This is a fixed support. In addition, dWdx at this support, right, x equal to 0, is equal to 0 as well. dWdx represent what? The slope, right? The slope of the beam. Right. So the fixed support, for a fixed support, both the displacement and the slope are equal to 0. So we have these two conditions for a fixed support. That's the left end. And the right end, this end of the beam, is a free end. There are no constraints on its displacement or slope. Right? That's a free end. Right. Pinned support or simple support. The support shown in this figure, right, is a pinned support or simple support. I note that pinned support fixes both vertical and horizontal positions. It fixes position, but not the slope. So this beam is still able to rotate around this support. So this is a simple support or pinned support. The right end shows a pinned support on rollers. Right? This is a roller. This support fixes the vertical position, but not the horizontal position or the slope. Right? So this support can travel in the horizontal position. It can move along the horizontal position, and this beam is able to rotate as well. Okay. So this support only fixes the vertical position, but not the horizontal position or the slope. So we introduced totally 4 types of support. Now in this class, we are going to focus on the fixed support, whose displacement and slope are equal to 0. Next, let's discuss types of loads. And here we focus on transverse loads. So we are going to introduce 2 types of transverse loads. First is called point load or concentrated load. F, that's force F, right? It's a total force. Newton is applied to a single point of the cantilever beam. So this is the point load or concentrated load. The force is concentrated at one point. The second type of transverse load is a distributed load, which distributes along the length of the cantilever. Right, Q. Right, this Q is distributed along the length of the cantilever. And the Q is a force per unit length, Newton per meter. Right? For the concentrated force, the unit is a Newton. Here, the unit of Q is Newton per meter. So in order to calculate the total force, we have to integrate Q over the length. A simple example of distributed load, right? The weight, namely the weight of the beam, right? The weight of the beam actually generates a distributed load. In order to calculate the distributed load due to the weight, let's consider this differential volume whose length is a dx, right? Then this is a cross-section area, right? So the volume of this differential element, I call it delta V, is equal to dx times W times H, right? That's the volume. Then the force, right, or the weight, right? The force is due to weight. Okay, the weight of the differential element, right? This element, delta F, is equal to delta M, the mass times the gravity, right? Mg, and the mass is equal to the volume dx WH times the density. Note that here rho is density of the material times g. Then Q, the distributed load, Q is a delta F over dx, right? The force per unit length, right? So from the above equation, then Q is equal to WH rho g, right? WH rho g. So we can say that this is a uniform distributed load. Right? Q is a constant. Questions? (1.3) Force balance and moment or torque balance. As shown in this figure, a point force F is applied to the tip of the cantilever. Then, as we can imagine, the cantilever will deflect downward. It will deflect downward and eventually reach equilibrium. Now you can imagine now you are standing on the tip of a diving board. Right? This cantilever is very similar to a diving board. Right? It's a kind of miniaturized version of diving board. Right? This board will deflect downward, but eventually it will reach equilibrium. How does a cantilever reach equilibrium? Based on Newton's law, right? First, there must be a force, a reaction force that counteract F, right? And this reaction force, Fr, can only occur at the fixed support, right? At this anchoring point. And the Fr must be equal to F, right? To balance this downward force, right? Fr is upward, this F is downward, right? They must be equal. Is this enough? No, it's not. Because this force also generates a moment which tends to rotate this cantilever beam. How large is the moment, force moment generated by this force? Right, M is equal to F times L, right, distance. Right? We choose this anchoring point as a reference point. Right? So the distance between the force to the reference point is L. Right? So the moment of torque is simply equal to the force times its distance to the reference point. So in order to balance this torque or moment, there must be a reaction moment, mr, and this mr should be equal to FL, right, to balance this FL. Then the cantilever can reach equilibrium. Doesn't this make sense to you? So in order for this cantilever to reach equilibrium, we have to reach both force balance and a moment balance. And we can say this moment F times L is clockwise, right? Direction clockwise. And this MR, the reaction moment, must be counterclockwise, right? To counteract this moment. So both force and the moment need to be balanced. Next, let's try to find out the internal force Vx and internal bending moment Mx. In the previous slide, we only discussed, we only find out the force and the moment occur at the anchoring point, right, at the fixed support. Next, let's find out the force and the internal force and the internal bending moment. For this purpose, right, let's hypothetically cut the beam into two parts at a position x. Okay, so this distance is x, right? The total length is L, right? Then what's the length of this part? This length should be L minus x, right? Its length should be L minus x. Now let's focus on the right part of the beam. Right, this is the hypothetically cut plane. Okay, the right part should be in equilibrium, right, because this is only a hypothetical cut. Right, it should remain in equilibrium. Then we conclude that there must be a force Vxr occurring along this hypothetically cut plane. This Vxr actually is parallel to this plane. So this force is actually a shear force. And this force must be equal to F. Right? Vxr should be equal to F based on Newton's law. Simultaneously, now the moment generated by F, right? Now we choose this plane as a reference point. So the moment generated by this force is F times L minus X, right? F times L minus X. Then there must be a bending moment on this surface, right? Mxr, which must be equal to F times L minus X. Right, so both force, right, as we just learned, both force and the moment should be balanced. And this is a very important result. We can say that first we can say the force, internal force or internal shear force actually is constant. It's independent on x. It's not a function of x. What happened to the internal bending moment M? right? It's a function of x. X over mx. When Lx equal to L, right? M is a 0, right? When x equal to 0, this is 0. M is a maximum. Right? So that's the distribution of mx along the length of the cantilever. And we can also verify this result by checking the left part. Let's see if the left part is also in equilibrium. Based on Newton's third law, right, mxl, right, the internal bending moment applied to the left plane must be equal to mxr. Right? These two bending moments should be equal, and vxl should be equal to vxr and equal to f. Right? These two forces must be equal, right? Based on Newton's third law. Then the total force experienced by the left part is Fr, right? It's upward force minus Vxl, right? And Fr is equal to F. Vxl is also equal to F. So the total force is 0, right? So the force is balanced. How about the total moment? So let's calculate the total moment experienced by the left beam. Let's consider the counterclockwise direction as positive, right? So the total moment is mr minus the torque generated by this Vxl, right? Vxl times x, Vxl times x minus mxl. So there are two moments here. And okay, let's calculate. Let's calculate this total moment. Vxl times x is equal to fx, right? Vxl is f, and mxl is equal to mxr. So that's FL minus x, right? This one equal to mxr. Now we add them together. That's FL, right? And MR is equal to FL. Right? MR is equal to FL. So we can see for the left part, both force and moment are in balanced, right? So the left part is also in equilibrium. Summary: for a transversely loaded beam, there are internal shear force Vx and internal moment Mx. Please note that we changed the symbol convention here, right? Previously we used Vxl, Vxr to represent the forces on the left plane and the right plane, and the mxl, mxr to represent bending moments on the left and the right plane. But it turns out, based on right, based on Newton's third law, right, they are equal. Right, so actually we can remove the subscript, right? Simply use a V and a M to represent the internal shear force and the internal moment. And Vx and Mx can be calculated using force balance and moment balance by hypothetically cutting at position X. Right? We just hypothetically cut the beam at the position X. Then by analyzing the right part, we calculated Vx and Mx. Note that later we are going to use this result again. So please keep in mind, right? This internal bending moment can be calculated, right, for this cantilever beam. Pure bending of a transversely loaded beam. Right, we just discussed, right, if we apply a force F to the tip, right, this cantilever will bend downward and reach equilibrium eventually. And what we are going to do next is to derive or calculate W, right, the displacement, as a function of X. Or namely, we want to know the shape of the deflected cantilever beam when a force F is applied. For this purpose, let's consider a differential section of the beam, right, this differential section. And this is the enlarged view of this differential section. Please know that this middle plane is a neutral plane. Right? We assume this is a homogeneous cantilever, so it's made from same material. So the middle plane is the neutral plane. On the neutral plane, there is no stress or strain, or the stress and strain are zero. Right? That's the reason we call it the neutral plane. Above the neutral plane, the material is stretched. Below the neutral plane, the material is compressed. Right, so that's a concept of a neutral plane. And from this figure, we can also observe that this rho, this distance, is the bending radius. And the d theta is the angle that corresponds to this differential section. So its corresponding angle is a d theta. Then let's consider a plane with a distance z above the neutral plane. Namely, this plane, this red plane. Its distance to neutral plane is a z, right? This distance is a z. And as we just said, the plane above the neutral plane is stretched, right? So its length is L plus delta L, or L plus dl. Please know that L is L is the length of this neutral plane. Right? This length. So it's equal to rho, the bending radius, times this angle. Right? So it's equal to rho d theta. And for this plane above neutral plane, right, its length is increased to L plus dl. Right? This dl is an increase, the change of length. Now let's draw a line. Okay, this line I highlighted using red ink. This line is parallel to this line. Then we can see that . this distance is L, right? Because the same as the length of the neutral plane. Right? These two sections are same. Right? They have the same length. And this small distance, the dl, namely the change of length. Then we compare this small triangle. Okay, there's a very small triangle and there's a large triangle. Okay, these two triangles are similar. So based on similarity, dl over L, right? dl over z, right? This distance is a z, right? dl over z is equal to this distance over this distance, right? So it's L over rho, right? This length is L, and this length is a rho, L over rho. So this equation is divided based on the similarity of these two triangles. And then we can switch L and Z, right? So the left side becomes dl over L. And we just discussed this a moment ago. dl over L is the mechanical strain, right? So the mechanical strain on this plane is equal to dl over L, which is equal to z over rho, right? Z over rho. Z is the distance to the neutral plane. Rho is the bending radius. That's the mechanical strain. And please know that mechanical strain epsilon is a function of x, the horizontal position x, and the distance to the neutral plane z, right? The thickness direction. If we know the mechanical strain, then we can calculate the stress based on Young's modulus. Right? Stress is equal to Young's modulus times the strain. Right? So it's z times E over rho. Based on this result, where is the maximum stress or strain along z direction? Very simple, right? We can say epsilon or sigma is proportional to z, right? Z the distance to the neutral plane. So on the neutral plane, epsilon and sigma are both 0, right? That's the reason we call it the neutral plane. And above the neutral plane, z is positive, right? So we have positive stress and positive strain and positive stress, and they are proportional to z. So the maximum stress and the maximum strain occur on the surface of beam, either top surface or bottom surface. That's why when we bend a stick, it cracks. It always cracks on the surface first. So this result is consistent with our everyday life experience. So the stress is linearly proportional to z, a linear function of z. And this figure plots the stress as a function of z, right? Z is a distance to the neutral plane. We can say that's it's a linear curve, right? It's a linear function. And this horizontal axis, we know that horizontal axis is a stress, sigma. This vertical axis is the thickness or the distance to the neutral plane, like corresponding to the thickness of the cantilever beam. Right? The total thickness is h. So z of the top surface is h over 2, bottom surface is negative h over 2. And we can see that above the neutral plane, the stress is a tensile, it's positive. Below the neutral plane, the stress is a compressive. And this internal stress leads to an internal bending moment mx. That's actually the origin of the internal bending moment mx. Let's calculate the internal bending moment generated by the stress, right? The sigma. Let's consider a layer with a distance z from the middle plane, right? Please note that this is a cross section of the beam. H is the height, W is the width, so this is a cross section. And we choose a layer with a distance z from the neutral plane, and its thickness is a dz, right? So a very thin layer. Then the force generated by this plane, let's call it dF, right, is equal to area dz times W times h. No h, my mistake. The area dz times W, right? Then times sigma. That's the force. Force can be calculated by multiplying the stress with the area. So the bending moment referring to the neutral plane, right, generated by this layer is dF times z, right? Force times distance. And dF is a dzw sigma, right? W dz times sigma, right? Times z. So that's the bending moment generated by this thin layer. And to calculate the total bending moment, we need to integrate this dm from negative h/2 to positive h/2. Right? Integrate from the bottom surface to the top surface. Okay. That gives us the total bending moment. Then we can replace sigma, the stress, with this expression. So it's a function of z. And another z here, so it becomes z squared, right? And this z, we integrate z from negative h/2 to positive h/2. So that gives us 1/12 WH cubic E over rho. Right? Rho is a function of x, the horizontal position. We replace 1/12 H cubic with I. Right? We call I the moment of inertia of the rectangular cross section with respect to the neutral plane. So in this case, I is simply equal to 1/12 WH cubic. This is I. The bending or the moment of inertia of the rectangular cross section with respect to the neutral plane. So this equation, right, relates the internal bending moment to the bending radius, rho x. We can rearrange the previous equation. 1/rho, the reciprocal of the bending radius, is equal to mx over EI. So this is a rearranged from the previous equation. This equation establishes the relationship between the radius of curvature, or bending radius, and internal bending moment mx. So it's a relationship between geometrical quantity, by rho, and the mechanical quantity, mx. But then the stress can be related to the internal bending moment. Right? Previously, the stress is a function of bending radius. Now we can replace the bending radius with mx. Right? So sigma can be directly related to internal bending radius. Similarly, the strain can be related to mx. Mathematically, the radius curvature can be related to the shape or displacement of the beam. Namely, 1 over rho, the reciprocal of radius curvature, is approximately equal to the second derivative of W, the displacement, with respect to x. Right? The second derivative of W with respect to x. Right? W is displacement. Please note that this is only true for small curvature, for small deflection. But then we end up with this equation. Right? The second derivative of W with respect to x is equal to mx over EI. Right? We replace 1 over rho with this second derivative. So we establish an equation that relates W, the displacement, to mx. Remember that our initial goal is to calculate the W, right? To calculate the displacement of the cantilever beam or the shape of cantilever beam. Now from this equation, we can see that we can calculate W if mx is given, right? So this is how we calculate Wx. Let's take a look. Let's take a look at one example. Bending of cantilever beam with a concentrated end load. We assume this force applied to the tip. Right? Please note that it's not necessarily applied to the tip. It can be applied in the middle, 1/3, or any arbitrary position. Okay. Now let's just simplify the discussion by assuming that this force F is applied to the tip. We want to calculate Wx for this case, right? Then we need to use this equation. Then we need to calculate mx, right? Internal bending moment. What's the internal bending moment for the cantilever beam under this case, right? Under this force? We actually calculated that in this slide, right? How large mx is equal to F times L minus x, right? It's a function of x. So mx is equal to, we don't need to calculate it again, right? We can use the result directly. Mx is equal to F times L minus x. So the second derivative of W with respect to x should be equal to F L minus x over EI. Right, so that's a differential equation. Then we perform integration on both sides. So the left side becomes the first derivative by dw dx. The right side, we have FL over EI times x minus x squared, right? Because we have x here. So after integration, it becomes x squared over 2EI plus A. Please note that A is the integration constant. How do we determine A? We need to determine A based on the boundary condition of this cantilever. But for this cantilever, the left end, namely when x is 0, this is the x-axis, and its origin is selected here. When x is 0, this point is a fixed support. Then its displacement should be equal to 0, right? W0 is 0. And its slope, dw dx, should be equal to 0. So let's use this boundary condition to determine A, right? Use this the second one, the slope, right? We set x to, right? X to 0, x to 0, and the slope should be equal to 0. How large is A? A must be equal to 0, right? Based on this boundary condition, right? The slope of the fixed support is 0. Then we perform another integration. So the left side becomes W, the displacement, right? That's what we want to calculate. And the FL over 2EIX squared, right? X become X squared. And this X squared become X cubed, right? So it's F over 6EI, right? After integration, we need to have 1 over 3, right? 1 over 3, 3 times 2 is 6. And the x cubed, right, plus b, another integration constant. And we can determine b based on this first boundary condition. Right, the displacement should be equal to 0, right, at the origin, at this fixed support. So we set x to 0. This w should be equal to 0. So how large is b? Right, b should be equal to 0 as well, right, based on this boundary condition. So both a and b are equal to 0. So finally, the displacement is equal to, or you can combine these two terms together, right? Wx equal to f times 3L minus x times x squared over 2EI. I is where's I? Right here, right? I is the moment of inertia, which is equal to 1 over 12 WH cubed. So where is the maximum displacement for the cantilever beam? Very simple, right? It occurs when x is equal to L, right? At the tip. So it's equal to F over 3L minus L squared over 6EI. Right, so you can finish the calculation by yourself. That's the maximum displacement of the cantilever beam. But we actually can calculate the displacement at an arbitrary position using this result. W is a function of x.
Sensors based on cantilever beams. Please note that a cantilever is a very simple mechanical structure and it can be readily manufactured using micro or nano fabrication technologies. Many sensors can be developed based on cantilever beams. It can be used to sense force, displacement, surface stress, temperature, mass, and so on. One specific example is a AFM cantilever, as shown in this SEM image, with a sharp tip integrated on the distal end. This cantilever can scan and obtain the surface profile with atomic resolution. Another example is the accelerometer. To function as an accelerometer, a proof mass is attached to the tip of the cantilever. Then when there is an acceleration, for example, in the downward direction, the proof mass will experience an inertial force. F is equal to ma. Right? This is based on Newton's second law. Right? Then the proof mass will deflect downward, and thus the acceleration can be measured by measuring the displacement of the proof mass or the deflection of the cantilever. How large is the displacement of the centroid of the proof mass when there is an acceleration A? Right, and let's assume the proof mass is rigid. Right, this proof mass is rigid. To answer this question, well, we have to find the deflection of the cantilever. So how do we find the deflection of cantilever? As we just discussed, we need to find the internal bending moment mx. If we know mx, right, then we can calculate the deflection of the cantilever. So the question is now how to find this internal bending moment mx. How do we find the mx? Actually, mx can be calculated by hypothetically cutting the beam at the position x. So let's assume this distance is x. And please know that the total length of cantilever is L. And the length of the proof mass is L sub m. Then for the right part to this dashed line, this internal bending moment mx. Right, in this direction has to balance the clockwise torque generated by the acceleration, right, by this inertial force ma. And the torque generated by this ma should be equal to ma times the distance, right? Distance from this centroid to this hypothetic cut. So how large is this distance? Right, so if you know the distance, right, then you can find the mx, then find the deflection of the cantilever, and then the displacement of the proof mass.